Hi there viewers, and welcome to this video which is looking at solving simple linear equations using two different models for equality, in particular in this case. And you can see what we've got set up here is a simple linear equation, the equation 3x plus 2 equals 20. And the model we're using here is a discrete or object view of equality where we have the 3x plus 2 on the left-hand side, and we've got 20 over here on the right-hand side. And you can think about this perhaps as a balance scale or something similar to that. It works in a very, very similar way, but I'm using algebra tiles to model this. And what we're going to do here is we're going to solve this equation by showing sort of what on the left is equal to or equates to what on the right. And so what we can see here is that I've got these two ones, and they must be equal to the two of these ones over here. And in the sort of standard parlance for equations, I can remove these ones from both sides because they're both equal to each other. And so what I have is that if these two parts are equal, then these two parts up here must be equal. But I can actually physically remove the ones by combining them with negative ones. And whether you actually choose to do this or not, then the result is the same, that actually what we've done here, whether we actually physically subtract the two from both sides or whether we just discount the twos, is we end up with the 3x's being equivalent to, being equal in value to 18 of the ones, the 18 remaining ones. And so now it's about, okay, well, if these 3x's are equivalent to these 18 remaining ones, how many of those ones is equivalent to each x? And what we can see here very quickly is by simply rearranging these ones so that they form three rows, just like the 3x's do, we can see that each of these x's must be equivalent to 6 of these ones. So we can almost, if you like, split this into 3 equal parts, and then we can split the ones into 3 correspondingly equal parts. And again, I could remove a load of these, although I tend not to when I'm modeling this because that's has links to subtraction. What I'm doing here in reality is splitting that 3x up into 3 equal x's, and so I'm dividing that 3x into 3 equal parts, and that means I've also split the 18 into 3 equal parts, and so each part will be equal to 6 of the ones. And this is how I might model the solving of this equation using a model where basically objects on the left are equal to an equivalent number of objects on the right, and that's why it's called, why you can think about it as an object or a discrete sort of representation of this and a discrete model for this. The potential slight issue with that is that the equality is somewhat has to be told. Basically, it's not implicit in the model itself. There's no reason why, just by looking at those two separate expressions, the one that was on the left of the line and the one that was on the right of the line, that those would necessarily have to be equal. You have to be told, I want these things to be equal to each other, equal in value. Obviously, if you're actually doing it on a physical balance scale, that's different because then you can tell when the things are equal. But using the tiles in this way, we have to make explicit that they're equal because it's not contained within the model. The alternative is to use a measure model for the equality, in this case using a bar model. And in this case, the equality is much more implicit within the model. The fact that these two lines, the top line and the bottom line, are of equal length, i.e. equal measure, makes the equality between the expression 3x plus 2 seen on the upper bit and the expression 20 seen on the bottom of the bar model there, it makes it, as part of the model, an implicit part of the model. In terms of the sort of way of approaching the solution and modeling the solution of an equation like this, it proceeds in much the same way. And the object versus measure or continuous view of this, there are pros and cons to each of them, as we'll see as we do more equation solving beyond simple linear equations. But the actual modeling of the solution here and of solving these types of equations proceeds in much the same way. We can see we've got the 3x plus 2 there. We can see we've got the 20 there. Well, then if we look at this 20, we can say, well, if I shorten that down to 18, I can think of that. Oh, let's get rid of the 20 first. I can think of that 20 as 18 plus 2, or I can remove the 2 from both the top and the bottom line, and we can see the lines are still equal. So that shows the 3x must be equal to 18. And then, of course, because this is 3 x's making 18, I can split this 18 into 3 parts. But now, of course, each part is 18 divided by 3, so each part is no longer 18, each part is 6, and we can see the equality there between x and 6. And with simple linear equations, there's nothing much to choose between these two models. Both models work, quite well. The bar model, the length model, can make it slightly trickier when the value of x is negative compared to the object model, but the object model has that issue that we talked about in terms of the equality not being quite as explicit, or not being contained within the model. It has to be an imposed part of the model. But both of them work in quite a number of cases to sort of help learners see why something like the equation 3x plus 2 can be manipulated in the way it can be in order to arrive at the solution. So hopefully that sort of made it clearer how you might use manipulatives or representations to support the solving of simple linear equations. And in later videos, we'll move on and look at some more complicated equations as well. As always, I'd like to say a big thank you to Johnny Hall at mathspot.com for his wonderful virtual manipulative site, which I've used to make this video. And I will see you again in the near future. Thank you very much.